Okay, so in class we learned about Doppler effect. This is meant to be supplement for people, if the first time going through in class wasn't enough, or if you were absent, this is a great way to not only just get the information, but also hear some of the instruction that went along with it. So Doppler effect terms. So you have to have a source, something that is actually making the noise. So in the case down below, that's going to be the car. Okay, or it could also be emitting a light, because both sound and light are types of waves. The observer is the person hearing the noise, so that could be person X or person Y. And then the wave fronts are these little lines these are kind of like, for a transverse wave, it would be a crest maybe. For a longitudinal wave, it might be the compression, all right? And then in between, like this, if this is the crest, then in here is the trough, and then this is another crest. All right? So you can also determine wavelength from here. All right? Or if it's longitudinal, then maybe this is a rarefaction, this is compression, that's rarefaction. But still, same thing, that is one wavelength. The Doppler effect. If the sources are stationary and the observers are stationary, then the wavefronts are evenly spaced on all sides, and observer Y doesn't hear or see anything differently from observer X. But if the object is moving, then that's when Doppler effect takes place, only with moving objects. Okay? Doppler effect, when an object moves, actually is the effect of the frequency changing based on the position of the source compared to the observer. All right? If the source is moving towards the observer, you're going to have small wavelengths at a high frequency. All right? Whereas, say, someone who is on the other side and the source is moving away from them, they see these really, really long wavelengths and low frequencies. Right? If you go to this link and watch the video, it's a little visual and motion thing that I just wouldn't have the first idea how to make in the first place. And it also connects this to the fact that how we know the universe is expanding. So a real-life application of Doppler effect. So Doppler effect. What happens if the source is moving away from the observer? Okay, so that's going to be this guy. He's moving away from him. All right. So what do you notice about the wavelengths? Since he's behind and the car is moving away, the wavelengths are getting longer. All right. And then we know that speed of sound is constant. So say this is a horn honking. So we know that if our speed is going to stay the same and we make our wavelength really big, what's going to happen to the frequency to keep the velocity the same? Your frequency has to be very small. Okay? So your frequency is small or low. All right? So, and pitch corresponds to frequency. Low pitches are caused by low frequencies. So you'll have a low pitch. Or in terms of light, low frequencies of light are red. Okay, so low pitch or with light you see red. So now let's think about the point of view of the person where the car is coming towards them. All right. So if you notice, now the wavefronts are a lot closer to each other, so we have a small wavelength. So again, if velocity needs to stay constant and our wavelength is small, that means our frequency has to be really big, so large. And again, pitch is going to correspond with frequency. High frequencies mean high pitch. And then for light, the high frequency end is violet or blue. All right. So just keep this, the big things to keep in mind are if the frequency is large, okay, so as it moves towards, the frequency has to go up. If it moves away, frequency has to go down. Towards, frequency has to go up. This is a big thing to remember. So, when the object's moving away from you, frequency goes down. If the object's moving towards you, the frequency goes up. Doppler effect equations. So, this complicated thing is the Doppler effect equation. All right? What you're doing is you're using an equation to find out what the new frequency, or the frequency that the observer is actually hearing when the object is either moving towards it or away from it. All right? So, the sound source is emitting a sound at a very specific frequency, like maybe 350 hertz or something like that. But its frequency based on the Doppler effect could be greater than that or could be less than that, depending on which side of the sound the observer's on. So v is the velocity of the wave. This is going to be a constant. For sound, that's going to be 340 meters per second, and that's what we'll use most often when we're working with this equation. Or for light, it's going to be 3 times 10 to the 8th meters per second. But we're going to stick to using sound in here just because it's an easier number to manage. And then VO stands for velocity of the observer, so the person actually hearing or seeing. And then VS is the velocity of the source, so that's going to be the thing emitting the sound or emitting the light. So, we can split this up into 4 different types of situations. We have the observer moving, and observer moving closer to a stationary sound. So if they're getting closer together, what should happen to the frequency? So as objects get closer together, frequency has to go up. So in this equation, the source is stationary, so Vs, our velocity of the source, should be 0. We can plug in a 0 for that. And then, since the observer is moving closer, frequency should increase, so that means this number on the top needs to get bigger. Alright? So this is what the equation looks like for this specific situation, when the observer is moving closer to a stationary sound. Okay? Sound is stationary, so there's no velocity. You get rid of it with a 0. The observer's moving closer, so we need to make sure the frequency gets bigger. And since the observer's on top, we want to add the velocity. So situation number 2. This time the observer's moving further from the stationary sound. So again, big thing to remember, our frequency has to be going down since they're getting further apart from each other. Again, source is stationary, so Vs is 0. Alright, and since the observer is moving further or away, the pitch should decrease, which means the frequency should decrease. So again, you just have the velocity of sound on the bottom, and then this time you subtract the velocity of the observer because you want to make the frequency smaller. Okay? So, but the only reason you subtract is because this is on the top of the fraction. Things get a little different when the source is moving. So, situation 3, our source is moving further from a stationary observer. So, source is moving further from the stationary observer. So now our observer is stationary, so VO is going to be 0. So we'll have just V on the top. And then since the source is moving further away, frequency must go down. Alright? So this time, because the velocity of the source is under the fraction, adding the velocity actually decreases the frequency. Okay? Because if you divide by a bigger number, that makes the number smaller. So this time, if it's the source moving further away, you have to add it. If it's the observer moving away, you have to subtract it. Last situation is 4. The source is moving closer to the stationary observer. So again, the observer is stationary, so that's going to be a 0. that since we're going closer, frequency has to increase. All right, so again, we have just the speed of sound on top, and then on the bottom, we'll have the speed of sound, and then it's going to subtract the source sound, because again, under the fraction, to make the number bigger, you actually want this number under the fraction to be smaller. Because if you divide by a smaller number, that leaves you with more number left. Okay? Alright, so first sample problem, we have an ambulance. So that's one thing. It's traveling at 25 meters per second. It's moving towards a man sitting on a bench. So which one is the source of the sound? That's going to be the ambulance, and the observer is going to be the man sitting on the bench. Okay? Then if the siren's original wave has a frequency of 200 hertz and a speed of 340 meters per second, what frequency will the man perceive as the siren approaches him? So if you list out your knowns, you know frequencies, 200 hertz. We already underlined that. We underlined speed. So our source, the ambulance, is moving at 25 meters per second. Something to add to this, it's moving towards or closer to the observer. And the observer is sitting on a bench, so his velocity is 0. So, key thing, since it's moving closer, f prime has to be bigger than f. So when we plug this into our equation, we have f prime equals 340, our VO is 0, over 340, and then we want to make sure that our f is going to get bigger. Sorry, I forgot to write the f in there, which is 200. So we want to make sure that 200 is going to be multiplied by something greater than 1, because that'll make it bigger than 200. So we need to actually subtract, because we're in underneath the fraction, so minus 25. Because then you'll have 340 over 315. Which will give you something greater than 1. Once you actually calculate that out, you can get around 215 hertz. Okay, second problem, very similar to the first one. We have an ambulance that's going at 25 meters per second, but this time we're going away from the man sitting on the bench. So again, our source is the ambulance, the observer is the person, and again, it's still 200 hertz of a frequency and still 340 meters per second. Key difference in this one is that this velocity s, our source velocity, is away. That means that f prime has to be less than f. So when we plug that into our equation, f prime, forgot the second line there, is 200 times 340 plus 0 over 340, and this time we want the denominator to be bigger than the numerator, so it ends up being less than 1, so we're going to add the 25 this time. If you do that and plug it into the calculator, you should get around 185 hertz. Set 3, you are walking home when you see a fire truck outside your neighbor's house. You run at 10 meters per second towards the scene to see the commotion. So we've got our source of the sound is fire truck. The you running, you're the observer. The fire truck sirens emit a sound wave with a speed of 340 meters per second and a frequency of 350 hertz. What frequency will you experience as you run towards the truck? Alright, so we've got the 350, we've got the 340. This time, the fire truck, it's already arrived to its destination, so it's not moving, so its velocity is 0, and your velocity is 10 meters per second, and you're getting closer. So since you're getting closer, f prime has to be greater than f. So we want to make sure that we're multiplying by something greater than 1. So when we plug that into the equation, f prime equals, 350 hertz times 340 on the top and 340 on the bottom. This time your 0 is plugged in for the Vs, and in order to ensure that the numerator stays bigger than the denominator, this time we're going to add the speed that you're running at, because that'll give you 350 over 340, which is greater than 1, and will increase the 350. If you do that, you get about 360 hertz. And the final problem. You are at the airport listening to a stationary engine of a 747. The speed of the sound waves is 340 meters per second, and the wavelength is 0.5 meters. If you run away from the plane at 15 meters per second, what's the frequency that you hear? So, source is the plane, you are the observer, and initially it seems like all you're going to have is frequency and some speeds, but you don't know your original frequency. However, we know this handy-dandy equation. So if we rearrange that to solve for frequency equals velocity over wavelength, so we can use 340 over 0.5, and that gives you 680 hertz. Okay, so that's how we get the frequency. And then, of course, you want to acknowledge the fact that you are running away from the plane. So you're going away, which means f prime has to be less than f. So if we plug that into our new equation, you're going to have 680 hertz times 340. Plug in for both v's. The source is moving, so the zero goes on, or the source is not moving, so the zero goes on the bottom. And then this time we want the the frequency, 680, to be multiplied by something less than 1, which means the numerator needs to be less than the denominator. So we're going to subtract our running speed. And if you plug that in the calculator, you get about 651 hertz. Alright, that's the end. Hopefully this helps if you're having any issues or if you've been absent. And I will see you in class.